Common programming concepts. This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust. But we will discuss them in the context of Rust and explain the conventions around using these concepts. So this chapter covers concepts that appear in almost every language. Okay. So specifically, you will learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program, and learning them early will give you a strong core to start from. Keywords. The Rust language has a set of keywords that are reversed for use by the language only. Much as in other languages, keep in mind that you cannot use these words as the names of variables. The Rust language has a set of keywords, okay, that are reserved for use by the language only. Much as in other languages, keep in mind that you cannot use these words as the names of variables or functions. Most of the keywords have special meanings, and you will be using them to the various tasks in your Rust programs. You will be using them to the various tasks in your Rust programs. And you will be using them to the various tasks in your Rust programs. And you will be using them to the various tasks. You will be using them to the various tasks in your Rust programs. Okay. A few have no current functionality. Associated with them, but have been reserved for functionality that might be added to Rust in the future. You can find a list of the keywords in Appendix A. Variables and mutability. As mentioned in the storing values with variables section, by default variables are immutable. This is one of many notches Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, you cannot change the value. To illustrate this, let's generate a new project called variables in your projects directory by using cargo new variables. Then in your new variables directory, open src main.rs and replace its code with the following code. This code won't compile just yet. We will first examine the immutability error. Okay, so let x5 and then it's immutable by default, but trying to change it, so it throws an error here. So save and run the program using cargo run. You should receive an error message as shown in this output. So cannot assign twice to immutable variable x. Yeah. So this example shows how the compiler helps you find errors in your programs. Compiler errors can be frustrating, but really they only mean your program isn't safely doing what you want it to do yet. They do not mean that you are not a good programmer. Experienced sessions still get compiler errors. The error message indicates that that the cause of the error is that you cannot assign twice to immutable variable x, because you tried to assign a second value to the immutable x variable. It's important that we get compile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs. If one part of our code operates on the assumption that a value will never change and another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. The cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler guarantees that when you state a variable, a value won't change. The Rust compiler guarantees that when you state a value, guarantees that when you state a value, when you state a value won't change. When you state a value won't change, it really won't change. So you don't have to keep track of it yourself. Your code is thus easier to reason through. But mutability can be very useful and can make a code more convenient to write. Although variables are immutable by default, you can make them mutable by adding mut in front of the variable name as you did in chapter 2. But mutability can be very useful and can make code more convenient to write. But mutability can be very useful and can make code more convenient to write. Although variables are immutable by default, you can make them mutable by adding mut in front of the variable's name. As you did in chapter 2, adding mut also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. For example, let's change src main.rs to the following. When we run the program now, we get this. Okay, so we are allowed to change the value bound to x from 5 to 6. We are allowed to change the value bound to x from 5 to 6 when mut is used. Okay, ultimately deciding whether to use mutability or not is up to you and depends on what you think is clearest in that particular situation. Quiz answer review. You answered 3. Okay, I actually did that before. Immutable means not mutable, not changeable. So constants. Like immutable variables, constants are values that are bound to a name and are not allowed to change. But there are a few differences between constants and variables. First, you aren't allowed to use mut with constants. Like immutable variables, constants are values that are bound to a name and are not allowed to change. But there are a few differences. There are a few differences between constants and variables. First, you are not allowed to use mut with constants. Constants aren't just immutable by default. They are always immutable. You declare constants using const keyword instead of the let keyword. And the type of the value must be annotated. You declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. We are about to cover types and type annotations in the next section, data types, so don't worry about the details right now. Just know that you must always annotate a type to constant. Okay, constants can be declared in any scope. including the global scope, which makes them useful for values that many parts of the code need to know about. Constants can be declared in any scope, okay, including the global scope. Okay, what makes them useful for values that many parts of the code need to know about. Okay, that's good. The last difference is that constants may be set only to a constant expression. The last difference is that constants may be set only to a constant expression, not the result of a value that could only be computed at runtime. Here's an example of a constant declaration. The constant name is 3 hours in seconds, and its value is set to the result of multiplying 60, the number of seconds in a minute, by 60, the number of minutes in an hour. By 3, the number of 3 hours we want to count in this program. Rust's naming convention for constants is to use all uppercases. Rust's naming convention for constants is to use all uppercase with an underscore between the words. Rust's naming convention for constants is to use all uppercase underscore and okay. The compiler is able to evaluate a limited set of operations at compile time. Compiler is able to evaluate a limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify, rather than setting this constant to the value 10800. See the Rust references section on constants evaluation for more information on what operations can be used when declaring constants. The compiler is able to evaluate a limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify. Makes sense. And then setting this constant value. Okay. So constants are valid for the entire entire time a program runs, within the scope they were declared in. This property makes constants useful for values in your application domain that multiple parts of a program might need to know about, such as the maximum number of points any player of a game is allowed to earn, or the speed of light. Naming hard-coded values used throughout your program as constants is useful in conveying the meaning of that value to future maintainers of the code. Naming hard-coded values used throughout your program as constants is useful in conveying the meaning of the value to future maintainers of the code. It also helps to have only one place in your code. You do need to change it if the hard-coded value needed to be updated in the future. It also helps you to have only one place in your code that you only need to change it for the value needed to be updated. So shadowing. As you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as a previous variable. Rustaceans say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any use of the variable name to itself until either it itself is shadowed or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. In effect, the second variable overshadows the first, taking any uses of any of the variable name to itself until either it is still shadowed or the scope ends. You can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. You can declare a new variable with the same name as a previous variable. You can declare a new variable with the same name as a previous variable. Rostations say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any uses of the variable name to itself until either it itself is shadowed or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. This program first binds the x to a value of 5, then it creates a new variable x by repeating let x equals, taking the original value and adding 1. By repeating let x equals, taking the original value and adding 1 to 1, so the value of x is then 6. Then within an inner scope created with the curly brackets, the third let statement also shadows x and creates a new variable, multiplying the previous value by 2 to give x a value of 12. When that scope is over, the inner shadowing ends and x returns to being 6. When we run this program, it will output the following. Shadowing is different from marking a variable as a mute, because we will get a compile time error if we accidentally try to reassign to this variable without using the let keyword. By using let, we can perform a few transformations on a value that have the variable be immutable after those transformations have been completed. Shadowing is different from making a variable as a mute. Shadowing is different from marking a variable as mute. Shadowing is different from marking a variable as mute. Shadowing is different from marking a variable as mute, because we will get a compile time error if we accidentally try to reassign to this variable without using the let keyword. By using let, we can perform a few transformations on a value but have the variable be immutable after those transformations have been completed. The other difference between mute and shadowing is that because we are effectively creating a new variable when we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by inputting space characters, and then we want to store that input as a number. That's nice feature. The first spaces variable is a string type, and the second spaces variable is a number type. Shadowing thus spares us from having to come up with different names, such as spaces underscore str. Shadowing thus spares us from having to come up with different names. Okay. Instead, we can reuse the simpler spaces name. However, if we try to use a mute for this, as shown here, we will get compile time error. Makes sense. The error says we are not allowed to mutate the variable's type. Now that we've explored how variables work, let's look at more data types they can have. Data types. Every value in Rust is of a certain data type, which tells Rust what kind of data is being specified, so it knows how to work with the data. We will look at two data types of sets, scalar and compound. Keep in mind that Rust is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we wanna use based on the value and how we use it. In case when many types are possible, such as when we converted a string to a numeric type using parse in the comparing the guess to the secret number section. In chapter 2, we must add a type annotation like this. If we don't add the U32 type annotation above, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. The compiler can usually infer what type you want to use based on the type and how we use it. In cases when many types are possible, such as we converted the string to a numeric type using parse. Because it can be number, but like a different kind of number types. Makes sense. Okay, that makes sense. You will see different type annotations for other data types. Scalar types. Wait a second, this was the data types. Is it data types? No, it's starting. Okay. So scalar types. A scalar type represents a single value. Rust has four primary scalar types: integers, integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Integer types. An integer is a number without a fractional component. We used one integer type in chapter 2, the U32 type. This type declaration indicates that the value it's associated with should be an unassigned integer. Signed integer types start with I instead of U. That takes up 32 bits of space. Table 3-1 shows the built-in integer types in Rust. We can use any of these variants to declare the type of an integer value. We can use any of these variants to declare the type of an integer value. Each variant can be either signed or unsigned and has an explicit size. Each variant can be either signed or unsigned and has an explicit size. Each variant can be either signed or unsigned and has an explicit size. Okay. Signed and unsigned refer to whether it's possible to the number to be negative. In other words, whether the number needs to have a sign with it, or whether it will only ever be positive and can therefore be represented without a sign unsigned. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or minus sign. However, when it is safe to assume the number is positive. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored using two complements representation. Each signed variant can store number from inclusive. Okay. where n is the number of bits that variant uses. So an i8 can store numbers from 2 to 7 2 to the power of 7 to 2 to the power of 7 minus 1. Unsigned variants can store number from 0 to 2 to the power of n minus 1. So a U8 can store numbers from 0 to 2 to the power of 8 minus 1, which equals 0 to 255. Additionally, the I size and U size types depend on the architecture of the computer your program is running on, which is denoted in the table as arg. 64 bits if you are on a 64-bit architecture and 32 bits if you are on a 32-bit architecture. You can write integer letters in any of the forms shown in table 3-2. Note that number letters that can be multiple numeric types allow a type suffix, such as 57U8. To designate the type, number letters can also use underscore as a visual separator to make the number easier to read, such as 1 underscore thousands. Okay, makes sense. So additionally, the I size and U size types depend on the architecture of the computer your program is running on, which is denoted as the table as arg. Which is denoted in the table as arg. Okay, arg. 64 bits if you are on a 64-bit architecture and 32 bits if you are on a 32-bit architecture. Okay. You can write integer letters in any of the forms shown in table 3-2. Write integer letters in any of the forms shown in. Okay. Note that number letters that can be multiple numeric types allow a type suffix. Can be multiple numeric types allow a type suffix, such as note that number letters that can be multiple numeric types allow a type suffix, such as 57U8 to designate the type. Number letters can also use as a visual separator to make the number easier to read, such as 1000, which will have the same value as if you had specified 1000. Which will have the same value as if you had specified 1000. Such as 1000, which will have the same value as okay. So how do you know which type of integer to use? You are unsure. If you are unsure, Rust's defaults are generally good places to start. Integer types default to I32. The primary situation in which you do use I size or U size is when indexing some sort of a collection. Also, when I'm indexing some sort of a collection, then I have to use I size or U size. Integer overflow. Let's say you have a variable of a type U8 that can hold values between 0 and 255. You have a variable of a type U8 that can hold the values between 0 and 255. If you try to change the variable to a value outside of the range, such as 256, integer overflow will occur. Yes, which can result in one of the two behaviors. When you are compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime. If this behavior occurs, Rust uses the term panicking when a program exits with the error. We will discuss panics in more depth in the unrecoverable errors with panic section in chapter 9. When you are compiling in release mode with the -- release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs two's complement wrapping. When you are compiling in release mode with the release flag, Rust does not include checks integer overflow that cause panics. Instead, if overflow occurs, Rust performs two complex wrapping. In short, values greater than the maximum value the type can hold wrap up around to the minimum of the values the type can hold. In the case of U8 type, the value 256 becomes 0, the value 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. Relying on integer overflows wrapping behavior is considered an error. Makes sense. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. Wrap in all modules with the wrapping methods, such as wrapping add. Return the non-value if there is overflow with the checked methods. Return the value and a boolean indicating whether these are overflow with overflowing methods. Signatures are saturate at the values minimum or maximum values. With these saturating methods. Floating point types. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust also has two primitive types. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust also has two primitive types of floating point number. Two types, okay. Which are numbers with decimal points. Rust's floating point types are F32 and F64, which are 32 bits and 64 bits in size, respectively. The default type is F64 because on modern CPU it's roughly the same speed as F32, but is capable of more precision. All floating point types are signed. Here's an example that shows floating point numbers in action. Floating point numbers are represented according to the IEEE 754 standard. The default type is F64 because on modern CPU it's roughly the same speed as F32, but is capable of more precision. Our floating point types are signed. All floating point types are signed. All floating point types are signed. Okay, there's no unsigned. Okay. The F32 type is a single precision float. The F32 type is a single precision float. And F64 has a double precision. Single precision float has a double precision. What? Numeric operations. Rust supports the basic mathematical operations you'd expect for all of the number types: addition, subtraction, multiplication, division, and remainder. Integer division rounds down to the nearest integer. The following code shows how you do use each numeric operation in a let statement. Each expression in these statements uses a mathematical operator and evaluates to a single value. Each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. The Boolean type. As in most other programming languages, a Boolean type in Rust has two possible values. As in most other programming languages. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are only one byte in size. Booleans are 1 byte in size. It means 8 bits. The Boolean type is in Rust is specified using bool. For example, the main way to use Boolean values is through conditioners. The main way to use Boolean values such as an if expression. We will cover how if expression works in Rust in the control flow section. The character type. Rust's char type is the language's most primary alphabetic type. Here's some examples declaring char values. Char is explicit type annotation. Note that we specify char letters with single quotes as opposed to string letters, which use double quotes. Rust's char type is 4 bytes in size and represents a Unicode scalar value, which means it can represent a lot more than just ASCII. Unicode scalar value, okay. Accented letters, Chinese, Japanese, and Korean characters, emotes, and zero with spaces are all valid char values in Rust. Zero with this emoji and zero with spaces are all valid char values in Rust. Unicode scalar values range from U plus 0 to U plus D7FFF inclusive. However, a character isn't really a concept in Unicode. So your human intuition for what a character is may not match up with what a char is in Rust. We will discuss this topic in detail storing UTF-8 encoded text with strings in chapter 8. Answer review. Okay, so Compound types. Compound types can group multiple values into one type. Rust has two primary compound types. Compound types can group multiple values into one type. Compound types can group multiple values into one type. Okay, Rust has two primary compound types: tuples and arrays. The tuple type. A tuple is a general way of grouping together a number of values with a variety of variable types, into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. We create a tuple by writing a comma-separated list of values inside the parentheses. Each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. We've added optional type notations in this example. The variable tup binds to the entire tuple, because a tuple is considered a single compound element. To the entire tuple. The variable tup binds to the entire tuple, because a tuple is considered a single compound element. Because a tuple is considered a single compound element. To get individual values values out of a tuple, we can use pattern matching to destructure a tuple value like this. Pattern matching. This program creates a tuple and binds it to the variable tup. It then uses a pattern that with let to take tup and turn it into three separate variables x, y, and z. This is called destructuring, because it breaks the single tuple into three parts. Finally, the program prints the value of y, which is 66.4. We can also access a tuple element directly by using a period, followed by the index of the value we want to access. We can also access a tuple element directly by using a period, followed by the index of the value we wanna access. For example, this program creates the tuple x and then accesses each element of the tuple using their respective indices. As with most programming languages, the first index in a tuple is 0. So the tuple without any values has a special name. The tuple without any values has a special name. Unit. The tuple without any values has a special name. Unit. The tuple without any values has a special unit. This value and its corresponding type are both written parentheses and represent an empty value or an empty return type. The tuple without any values has a special name. Interesting. Expressions implicitly return the unit value. Expressions implicitly return the unit value if they don't return any other value. Expressions implicitly return the unit. Expressions implicitly return the unit value if they don't return any other value. Expressions implicitly return the unit value if they don't return any other value. The array type. Another way to have a collection of multiple values is with an array. Another way to have a collection of multiple values is with an array. Unlike a tuple, every element of every array must have the same type. Unlike arrays in some other languages, arrays in Rust have a fixed length. Okay, so about this array type, let's do this next time.